and thanks to my committee and all the attendees. So I'm going to mostly talk about my thesis, which is model interpretation and data valuation for machine learning. I was very lucky to be advised by Professor James Sill. So as the name suggests, the thesis kind of has two parts and the talk is going to have two parts. So the first part is data valuation, where I'll talk about this notion of kind of fair data Shapley value, and then some of the applications it has. Then I'll end with this new notion of distributional Shapley value and how it can help. Then I'll move to the second part of the talk, which is machine learning interpretability. And then I'll talk about the very first project I did in my PhD, which was to show that many of the existing interpretability methods for deep learning models are fragile. And I'll finish briefly talking about a concept-based interpretation method that we developed. So let's start with data valuation. I'm going to begin the talk with a very simple example. So assume you have an AI for health company, which there are a lot of these days, and your task is to detect melanoma. So you want to build a model that looks at skin disease images and detects whether it's healthy or it's a melanoma lesion. So you have gathered your own data set and you have labeled it using the methodologies, and your model's performance is not that good. So what you naturally would do as a next step is to go and buy more data, to add data to your data set to make it bigger. So you go to a hospital, ask them for more melanoma images, they give you the images, you train your new models, and you see that the performance has improved to around 80%. The problem of data valuation is about basically assigning credit to different sources of data. So if you are the AI for health company, you would be like, okay, so this data only added 20% to my performance, so it's only responsible for that part. If you are the hospital, you would say, well, our data set alone would do much better than 20%. So we want to see what would be an equitable way of assigning value to individual sources of data. And this problem has become more and more important recently, as you might know. So the governor of California, Gavin Newsom, has called for this notion of data dividend, that companies like Facebook that use user data as labor should pay people. Or even there was a Senate hearing about this issue. So the problem is becoming more and more important for everyone. So making things a bit more formal, let's think about a machine learning problem. So any machine learning problem has basically three parts. You first start with a training data set that you have. So here we have kind of schematically shown with 3 points or 3 sources of data. You feed your training data into a learning algorithm. So you can assume it's SGD for a deep neural network or the fabulous CART algorithm for decision trees or anything else. It's just an algorithm that takes training data as input and it spits out a trained model. And finally, once you have a model, you should kind of basically measure how good it is. So you use a performance metric. So sometimes it says accuracy, mean squared error, or even if you're, let's say, a trading company, the revenue your model generates in the market. So any sort of metric that says how good your model is. What we want is to look at this basically performance of the model that is trained on your training data and find how much each of the sources of data contributed to this performance. So as an example here, you can see that the Pentagon has contributed a lot of information, while the star has not contributed a lot. But there are infinitely many ways to basically divide the model's performance among individual sources of data. But the one we are looking for is equitable data valuation. And we have to define what we mean by equitable. And we used the existing famous collaborative game theory literature to define the properties. So the first property is a null element property, which is a very intuitive one. So it defines what kind of data should get no value. So if you have a data point that is useless in the most extensive kind of case possible, so it's completely useless, meaning that if you take any subset of your training data and add this data point, the performance would not change at all. That data point should get 0 value, obviously. The second condition is the symmetric condition. So assume you have 2 data points that are virtually kind of similar or the same, meaning that if you take any subset of your training data and add either of them, the change in performance of the resulting model would be equal. Naturally, these two data points should get equal value for fairness. And the last condition is the linearity condition. So it's more of a machine learning specific property, meaning that if your overall performance metric is a linear combination of individual metrics, that linearity should be preserved in the value. So a very famous performance metric is test accuracy. It's just the sum of individual kind of test accuracies on individual training points. You want the linearity in your measure to be preserved in the value. So if you go ahead and compute the value of each data point for each individual test point and sum these values up, it should be equal to the overall value of each of the training data points. Now, assume I have a training data set, let's call it D, and it has M data points in it. And for simplicity, I'm gonna choose one data point, Z, and name every other data point in my training set as B. So I have M training data points, one of them is Z, and the M-1 other data points, I call them B. So what we showed in our work is that there's uniquely one value that satisfies the three properties. And for the people who are familiar with it, it's basically the Shapley value. And the formula might seem a bit complex, so I'll go over it. So the value of data point Z, the data Shapley value of data point Z, in the context of data set D is this. Assume S is just any random subset of B. So it's a subset of your training data that does not contain Z. We train a model on S and look at its performance, let's say test accuracy. Then we add Z to S and train another model. This difference would be the marginal contribution of data point Z to the subset S, AKA leave-one-out score of Z with respect to S. We normalize this score by the number of subsets that have the same cardinality. So a number of subsets of B that have equal number of members like S. And then sum these normalized marginal contributions for all of the subsets of B. In other words, it shows that basically on average, on like a weighted average, how much data point Z contributes to a random subset. There is an alternate formulation for the data Shapley value, which might be more intuitive. So it's basically the expected leave-one-out score with respect to all possible sizes, all possible cardinalities of data. So this is basically a random uniform sampling of 1, 2, 3 to n. And the second part is basically the expected leave-one-out score of Z with respect to subsets of data that have size k minus 1. So we are done with our first goal, which is we have defined this equitable measure of data value. So what's next? Well, this seems like a very informative measure because you're looking at the data points marginal contribution to many different sizes of data, so under many different contexts. So it should say how good or how bad a data point is or how useful it is. And that's exactly what we did. So as the first application of the data Shapley value, assume a very simple setting. So you have a naive-Bayes model, and the task is a spam classification. So what is the problem with your task? The problem is that 20% of your training data is mislabeled. So the labels are basically flipped, which happens a lot in real-world scenarios. And your goal is to correct the mislabeled data points. So you want to go over your training set and examine data points one by one and find the data point that is mislabeled. So the first approach is the most basic approach, which is you basically randomly search your data set and correct every data point that's mislabeled. And as you can see, in order to fix the whole data set, you need to basically go over the whole data set. But we remember that if a data point's Shapley value is small, it means that it's a bad data point. And also a noisy data point is a bad data point. So the second approach is this. You compute the data Shapley value of all of your training points. You sort them from the least valuable to most valuable. So in other words, from worst to best, and inspect in that order. And you can see that by inspecting around half of the data set, you have already found all of the data points that are mislabeled. And a lot of them are actually in the first 20% of low value data points, which is kind of expectable. But at the same time, you can see the fact that data Shapley looks at the marginal contribution on all possible sizes of data makes it a very robust value. So the regular leave-one-out score just doesn't work in this scenario. But let's examine deeper what it means for a data point to have a very high positive value and very high negative value. So assume we have a breast cancer prediction task, and we have 1,000 training data points, and we train a logistic regression model. What is the experiment we want to run? We want to delete data points one by one, and each time train a new model. So we are shrinking the size of our training data one step at a time. And each time we train a new model, and we test that model on a out of sample data and unseen data. So if you remove data points with random order, obviously the performance is going to drop because you're just making the size of your training data smaller. But it's not going to drop that much because the logistic regression model kind of saturates very fast in the number of data points. But if you start removing data points from the highest value to the lowest, so start removing your most important training data points, what you can see is that by removing less than half of the data points, the model is already kind of under random prediction accuracy. So the model is basically dead. So what this means is that that subset of data point that get a very high positive value, those are basically necessary for the model to work. That was kind of a new observation. But a more practical scenario or more useful
Amirata,
yes.
in the previous plot, could it have been the case that the initial points that you moved actually caused a slight boost in performance?
I mean, I'm not seeing something like that in the plot. Do you see something like that?
Oh, okay. So in the blue part, like
yes.
its initial part is not like slightly above the okay. No, sorry.
I mean, that's a good point. I think it's because of the random initialization of the model, we get a slightly different. A more practical scenario is that you want to basically curate your data set, or you want to repair your data set. So you sort data points from least valuable to the most valuable, and you remove them one by one. And as one might expect, the performance actually improves. So you're basically removing bad data points. So here we have removed almost half of the data points. The model is actually performing better. And you can see the original Leib-Banach score kind of matches with data Shapley and then stops working. So the data Shapley seems like a much more robust measure of an intrinsic value of the data. And turns out this has actually become some sort of a standard for other people to use. So I saw this paper in last year's ACL, which they got a state-of-the-art results for an NLP task just by removing bad data points. So not training any new model, nothing else, just by basically filtering their data set. And we did somehow the same thing. So in a collaboration with C. Tang, we looked at the chest X-ray data set, a famous one, famous for having mislabeled data points in it. And so first of all, we were able to detect kind of noisy data points by looking at the value. But we saw another application of the data Shapley value, which was you can basically interpret your data set and kind of find out some sort of potential pathologies. So this data set, the task is pneumonia versus healthy. And interestingly, we found there is a part of data points that are mislabeled as pneumonia, so they don't have pneumonia, but they get high Shapley value, which is weird because you explain the data point which is mislabeled to have low value. But inspecting these data points deeper, we realized that these are data points that don't have pneumonia, but actually have some other sort of anomaly. So, and that's why, because the model is just trying to detect healthy versus pneumonia, anything that's not healthy is helping with that model in the end. So this kind of shows some sort of potential pathology with this model. So your initial goal is pneumonia versus healthy, but the model is basically doing healthy versus not healthy, just because the way your training data works. And the last application is domain adaptation. So domain adaptation, for those of you who are not familiar, is a very simple scenario, but a very real world scenario. The scenario is that the training data you have has some differences with the test data you care about. And the example here is actually a very famous fairness problem case. So the training data is LFW, which is a very famous face data set. And the task is to detect gender given the face images. So when you train a model on LFW and test it on LFW, it gets around 97% accuracy. But there is another data set which is called PPB, which is designed to be equally representative of different skin colors and different genders. So it's a diverse data set. The performance of a model trained on LFW drops when you test it on PPP. Specifically on Black females, it drops to around 50%. So from 97% accuracy to around 50% accuracy. So how can we use data Shapley? It's a very basic idea. So we compute the data Shapley value of our training points, using a very small subset of samples from the target data, so around 30 to 50 samples. And we remove anything that gets negative value, meaning that we remove anything that's not helpful with the task. And we reweight data points that are left with a relative value, meaning that if a data point gets a very highly positive value, it's a very useful data point. So we assign more weight to it in the empirical risk minimization. And after doing that, the performance improves. And when we inspect kind of how the value relates to the original data point, all the data points that get negative value are white and male. And the top 20% of data points that get positive value are all female. So the idea of data point reweighting seems to be working in this scenario. There can be a more kind of different application of it, which is using cheap data. So here again, the target data is HAM 10,000, which is a data set created by dermatologists using dermatoscope and labeled by dermatologists. It has lesions of 7 different classes. So it's a very expensive data set to gather. This is a data set that I created in 3 hours doing Google image search of these diseases in Google. So you can see it's a very bad, noisy data set. And with 50 examples of this test data set, so we have enough money to just buy 50 examples. And applying our data Shapley adaptation method, we managed to improve the 7-way classification performance around 8%, which, assuming it was kind of almost with 0 expense, is not that bad. So those were the applications of the data Shapley. What are the potential problems with it? So problem number 1 is quite obvious. So if you look at the definition of the data Shapley value, it's NP-complete to compute because it's looking at every subset of the training data. But I showed results from the data Shapley. So how we did it, we use approximation. So what is approximation approach? So if you look at this definition, the data Shapley value of point Z is basically a mean estimation problem. So you have this random variable, which is leave-one out score of Z with respect to some random subset S. And if your performance metric is bounded, let's say it's test accuracy F1 score, this random variable is bounded. So you are doing the mean estimation of a random variable, so you can use all of the existing concentration bounds to have a good estimation of that random variable. And that's exactly what we did. And we created basically an efficient implementation of this method. Using parallel processing, we were able to compute data Shapley value for any model that was not a deep neural network and for data sets of size on the order of tens of thousands. And we call it truncated Monte Carlo Shapley. And that's what we have been using in our experiments. There's a problem number 2. The problem number 2 is that if you look at the definition of data Shapley value, it's been fixed. It's defined for a fixed training data set. So it's parameterized with a fixed training data set. So the value of this data point only has a meaning in the context of this specific training data set. So first of all, this notion is very game theoretical and it's kind of disconnected from machine learning in the sense that in machine learning, we always assume the training data we have is just a random realization of an underlying data distribution. And that kind of doesn't exist here. And it creates some problems. So first of all, if I have my training data and just add 1 point to it or remove 1 point to it, I have to recompute everything because the game has changed, the Shapley value has changed, which basically doesn't make much sense because if you have a data set of 1 million data points and you know the value of your data points, adding 1 point shouldn't change that much. It also doesn't kind of say anything about the value of new unseen data. So if you have a training data of, let's say, cat images, and you know the value of all of the data points there is 0 information about a new cat image that you can give, which still is not good. And it has some practical problems. For instance, going back to our initial example, the data Shapley value can only work for a buyer-seller setting if the seller first completely gives their data to the buyer, and the buyer computes their local data Shapley value, and the buyer will kind of return their computed value. And there are many incentives for the seller to just not share their value first, their data first. The second problem is that each buyer will have their own data Shapley value. So there is no generalizable notion of value for data points here. So buyer one will compute his or her own data value, buyer two the same. So this is a problem. We need a more intrinsic way of assigning value to these data points. The best scenario is that the seller that has so many data points with the same distribution as buyers would be able to compute their own local value, which would generalize to buyers. And in a collaborative work with Michael Kim, what we developed was distributional Shapley value. So instead of having a fixed training data set, this time you have a data distribution. So what's the definition of distributional data value? So again, for a data point Z, in the context of data distribution D, for data sets of size M, this is the definition of distributional Shapley value. And it's a very interesting definition. So it's basically the expectation of the data Shapley value of Z in the context of random data sets. So you can assume that if I sample M-1 points IID from D and add Z to that to have my own random data set, that would be a random variable. And the expected value of that random variable would be the distributional Shapley value. So why this specific definition? First of all, it still satisfies statistical variance of the three equitability properties we mentioned before. And you can also compute it efficiently with very similar Monte Carlo estimation methods. So we kind of solved that problem in the sense that now instead of having a fixed data set, we have a data distribution and the value is defined in the context of distribution. So what can be its use cases? So one of them is a very intuitive proposition. So assume two data points have very similar values. The two data points are very similar. We expect their values to also be very similar. And by that, more formally, we mean this. So assume I have points Z and Z prime that are very close to each other. Their distributional Shapley value should also be very close to each other. So some sort of ellipsis stability notion for the value itself. So in the work, we had like theoretical results that showed that for like regularized empirical risk minimization for RKHS, this is true. But in practice, for most of the models we tried, still this was present. So you had ellipsis stability of value in practice. So how can it be used? Assume I have a very large.
Amirata, yes. Quick question. Under what notion of distance was that?
That's a very good question. So some notion of distance. So assume you have some representation of space. So if it's images, let's say you have some space where the distance kind of has a meaning. Wherever you're computing your data Shapley values. So the interesting use case is value interpolation, which will change the problem of computation to inference. So assume you have a very large database M, large enough that it will approximate your data distribution D. And you want to compute the distributional Shapley value of all of the points in M. So that would be very expensive. Instead of that, you can take a large enough subset of S, an epsilon cover of M. And for the points in S, compute the distributional Shapley values there. Once you have done that, for every other point in M, you can interpolate, you can basically estimate its value by interpolating the value of the points in S. And for a more machine learning notion, you can basically compute the value for a subset of your data and then train a regression model to predict the value for every other data point. So this will make a computation much faster because for a large portion of your data points, you're not going to exactly compute their value. But at the same time, after having this interpolator or this regression model that predicts value, you can estimate the value of the points someone else gives you. So assume you want to sell your data, you have a very large database, someone comes to you and tells you like, okay, assign value to my data. You will be able to do that. So both the buyer and the seller will kind of have the same definition of value. And as one application in a collaboration with Salesforce Research, we use this notion to do active learning. So active learning is a setting where you have a fixed budget to label points given a large unlabeled pool. So assume you have 1 million unlabeled data points and you have budget to label 1,000. The goal of active learning is to select the subset of points that will result in the best performing model. And our idea is that we use kind of this value interpolator to approximate the value of unlabeled points and basically filter the unlabeled pool. For any point that gets very low value, we just throw it away from the unlabeled pool. And we use this in scenarios where the unlabeled pool is noisy, and it turned out that it can decently help. So we're done with the first part of the talk with the data valuation part. So as we showed, the data Shapley value uniquely satisfies equitability axioms, and we were able to create efficient algorithms to estimate it. But apart from that, it can be used for many applications like data set repair, domain adaptation, active learning, and etc. Distributional value of data basically bridges the gap between the game theoretical notion of Shapley value and machine learning. And at the same time, it can help us to have a more realistic scenario of buying and selling data and assigning value to data. Let's go to the second part. Machine learning interpretability. So what's the goal of interpretability? Assume I have two individuals and their features, and I use two machine learning models, one to give them insurance and one to give them loan. And they both get denied for insurance and one of them gets the loan. Intuitively, they should have the right to ask why, but at the same time, it's becoming a legal issue too. So legally, they should be able to ask why. And this why question and the answer to it is the problem of interpretability. So assume this is the insurance model, this is the loan model, and they seem very simple models to interpret. So we can see that David was denied why because he had accident history. Jennifer was denied why because she was young. Why did Jennifer get a loan? Because she was born on Valentine's Day. So the interpretation might not be acceptable, but it's true to the model, and that's what we want. But if the model is not as simple as the models in the previous slide, so if, let's say it's an Inception V3 model, that's a very good image classification model with 24 million parameters and 48 layers, what should we do? So these models are pretty good for a question that I refer to as the what question. So you give it an image or any other modality of data and ask it what it is. And it tells you the right answer with high accuracy. It tells it's a llama. But interpretability is the why question. So why does it say it's a llama? And existing methods basically work based on the idea that, okay, this model is very complex. We cannot kind of explain this one, but locally we try to approximate it with a, let's say, a linear model, a more interpretable model, and try to interpret this model just locally. So what kind of why questions we can ask? So the first one is that which one of the input features is very important. So I have this image, where does the model look at to say it's a llama? And you get answers like this. So it's a saliency map that says like these parts of it are important. And when you look at the original image, it makes sense, like it's looking at the llama. But at the same time, you can ask which one of the training examples affected my model such that this is predicted as a llama. So sample importance methods. And you get answers like this. So these three training examples had the most effect. But our question was different from kind of developing a better method. We wanted to ask the question of robustness. So why does robustness matter? Assume a hypothetical, not that hypothetical scenario anymore, that you have a machine learning model that's working as a judge. So you have a defendant trying to defend themselves and they have their own profile and the model says the defendant is guilty. And obviously the defendant should be able to ask why. And the model refers to their criminal background and their crime as the main reasons, which is an acceptable explanation. It makes sense. Like you should become guilty because of your crime. But assume we have a smart defendant that perturbs his or her profile, such that the profile is not that different. And even the AI judge has the same decision made. But then ask the why question, the interpretation doesn't make any sense. So the model says that because of their sex, race, or job, I said they're guilty, which is unacceptable. So the defendant managed to fool not the model's decision, but the model's interpretation. And this will debunk the whole model. So how can we see if we can attack model interpretability like that? The idea is that for an original interpretation and a perturbed interpretation, we want to maximize their boundary difference. So assume I have my test. So this is the llama image. This is my test input, and N is my neural network. I is my interpretability vector. So if it's a feature importance method, it's a vector with the number of features. If it's a sample importance method, it's a vector with the number of training examples. So it says how important is training example one. So I perturb my input with perturbation delta, and I look at perturbed inputs interpretation. Then I look at how different they are. So this is the measure of difference. Then I try to maximize this difference, but I cannot have any delta because I don't want my attack to be discovered. So first of all, there are two basically constraints. So first of all, delta should be bounded. So if it's an image, it's usually bounded in L-affinity norms such that visually they are very similar. So xt and xt plus delta are visually similar. But at the same time, I don't want the prediction to change, to not raise any suspicion. So I want the model to still give the same prediction. I want the input to still look very similar to human eye, but I want the interpretations to be very different. Is that possible? So what we did in our work is that we created algorithms that can solve the above optimization problem for deep neural networks. And these were the results. So you can see that for three famous interpretability methods at the time, we can take one original image and solve the optimization problem and get a perturbed image. So they look almost exactly similar to human eye. The model kind of still has the same monarch prediction, but the interpretation doesn't make sense anymore. So the original interpretation is looking at the monarch. The second interpretation is nothing the same. So at least the feature importance interpretability of deep neural networks is fragile. What we also applied kind of the same notion to sample importance interpretability. And you can see that again, for two images that look very similar, the most important samples that affect the model's decision can be very different. So we are able to fool sample importance methods too. For the last part, I'm briefly going to talk about kind of the notion of concept-based interpretability and basically just kind of the results we got. So I'm not going to get deep into the method. So again, we have our inception v3 model. We ask the what question, and it correctly says it's a taxi. And then naturally, we ask the why question. And as I said, existing feature importance methods give an answer like this. So they show which part of the input image is important. And as you can see, it's kind of looking at the wheels and the asphalt. It's kind of making sense. But this is not how humans communicate. So humans say taxis have wheel, taxis are yellow, taxis are on asphalt. So we wish the model to give interpretations like this. So to tell us this is a taxi because it's yellow. And we created this algorithm called ACE, so automatic concept-based explanations, which I will not get deep into, but we get results like this. And we think that these kind of explanations should be the future of at least explainability for deep learning models. So assume I ask the model what concepts are important for detecting a policeman, and the model says that, okay, so the most salient concept is a wheel. Well, it makes sense. The second most salient concept is kind of the writing, like the police writing on the van. And the third important concept is like the window, any window, like car window or like building window. And it can actually help us to find some pathologies with the model too. So when we looked at class basketball in ImageNet, we see that the ball itself is the second most salient concept. The first most salient concept is actually player's jersey, which if you think about that data set, it makes sense because all of the basketball images have basketball players in them too. And there's no way for the model to figure out which is the ball. It's just kind of, this is basketball. So, and the only class in the ImageNet that has basketball jersey is just the basketball class, or has basketball floor is the basketball class. So it can give us some interesting results regarding pathologies. So this was kind of my talk regarding interpretability. So the conclusions is that existing gradient-based methods for interpretability, both sample importance and feature importance, are not robust. And using these automatic concept-based methods might help us to get better understanding of neural networks compared to existing interpretability methods. So as my final kind of technical slide, this was